I was just watching a video of quantum mechanics, and I think every time I watch a new video on how it works, I just get more confused. And I think I cannot count how many different videos I've watched of just the double slit experiment, and every time I see one, it's as if a whole new concept. But in the video I just watched, they were trying to show that the light actually takes all possible paths, and then the path that it eventually takes is the one that we see. And that's how quantum mechanics work, that it takes all the possible paths that are present, infinite paths, and then the one that it eventually takes is the one that makes the most sense to it. It's like the interference pattern. So most of the paths that we do not see cancel each other out, and the one that we see are the ones which made the most sense. I don't know, it's just somehow difficult for me to wrap my head around it.
Yeah, quantum mechanics is wild like that. The more you learn, the more you realize how counterintuitive it is. The idea you're describing is related to Feynman's path integral formulation of quantum mechanics.
Mm-hmm.
In simple terms, it suggests that a particle, like a photon in the double slit experiment, doesn't just take one path from point A to point B, it actually takes all possible paths simultaneously. But when we observe the outcome, what we see is the sum of all these possibilities, and the ones that interfere destructively cancel out, while the ones that constructively interfere are what we detect. It's completely different from how we're used to thinking about motion in the macroscopic world. In classical mechanics, a ball follows a single predictable trajectory. In quantum mechanics, the ball theoretically explores every possible trajectory, but in the end, the observed path is determined by a probability wave. This is why quantum mechanics feels so bizarre. It operates on probabilities, interference, and superposition, which go against our everyday intuition. You're not alone in feeling like every new explanation makes it feel different. That's because different interpretations try to simplify it in different ways, but at its core, quantum mechanics is deeply weird. The way I think about it is, rather than a particle traveling through space like a tiny bullet, it behaves more like a wave of probabilities that collapses when observed. The path integral method is just another way of calculating which path is most probable based on how these probability waves interact. Does this version of it make more sense to you, or does it still feel strange?
It is strange, that's no doubt about it. And exactly the Feynman's thing, this is what I watched. And even though I thought, okay, these are just mathematical operations and whatnot, I was finding it hard to believe. Like, I always find a lot of things hard to believe in quantum, or I may want to think of alternative explanations to them might exist. But then he showed an experiment where the light does reflect from everywhere. And then he said if it's an LED light, which is usually just pointing in one direction, it should not be reflecting so much. And he showed that it did reflect from the complete surface. And the pattern of in the destructive and constructive waves were even seen. And I think that's just so crazy. And that just proves everything. That, yeah, it is trying to take every possible path that it can. But the implication of it is just so hard for me to even comprehend. I can imagine that light functions this way. But what else? What else would start functioning this way? Does that even confirm that the multi-universe theory is correct? And let's just say I stick to the truth, that the truth is that it is trying to take every possible path. And the path that we have observed is the one that was the best path to take. But then, how is it that you say that if it's the observed path, because it is taking all the paths. And when he tried with the light thing, he could even see the other paths. But without the experiment set up, he could not. So the observation is the conclusion is that it's not just simple way of observation, but it does take all possible paths, and the one that we are observing is the one which was more probable. Or maybe I'm confused, but that's how I think now, at least.
You're absolutely right. It's mind bending, and it feels like the more we try to grasp it, the more elusive it becomes. The implications of Feynman's path integral and quantum mechanics in general are far reaching and deeply unsettling when we try to reconcile them with our everyday understanding of reality. Breaking it down, what you just described. 1. Light and everything quantum takes all possible paths. This isn't just a mathematical trick. Experiments show that paths we usually don't consider actually contribute to the final outcome. 2. We observe only the most probable path, constructive interference. The paths we don't see are still real in some sense, but get canceled out by destructive interference. 3. Observation doesn't choose the path. The math does. We don't force the light to take one path just by looking at it. The system itself naturally evolves in a way where we only see certain paths. So what does this mean? If everything at a fundamental level behaves this way, then it's not just light. It applies to electrons, atoms, and theoretically, even larger objects. This suggests that our reality emerges from a deeper probabilistic nature rather than fixed trajectories like in classical physics. The multiverse idea could stem from this. If every possibility exists before collapse, does that mean every possible reality exists somewhere? Does this support the multiverse? The path integral approach doesn't outright prove the multiverse, but it does hint at the fact that every possible outcome exists until probabilities resolve into what we observe. In some interpretations, like the many worlds interpretation, instead of some paths canceling out, they all exist, but in different realities, leading to the idea of infinite branching universes. However, this is an interpretation, not something Feynman's math forces us to accept. Why this is so hard to accept? It's difficult because we have never lived in a world where things behave like this. If you throw a ball, it doesn't take all possible paths and land in every possible place. It follows one predictable trajectory. But at the quantum scale, things behave like this. And when scaled up, it somehow averages out into the classical physics we experience. So you're right in thinking this is wild. It absolutely is. The biggest challenge is not just understanding the math, but accepting that reality at its core is so different from what we intuitively believe. It's like peeling back a layer and realizing the universe is far stranger than we thought. But I love how you're approaching it, asking what else might work this way, questioning the implications. That's exactly what great physicists do. Do you feel like this framework makes it a bit clearer, or is there another part that still feels contradictory?
I think we have all agreed that it is feared and it will keep confusing me because what we cannot see, we cannot understand. But I want a bit more of an explanation of what I'm missing. We understood based on the description that, okay, we try to take all possible paths. But can you think of something that the physicists haven't yet found out, but is possibly true? I'm just throwing the ball in the air and trying to imagine or wonder what are the things that we have not yet considered, which might explain everything, or which might be something that nobody has yet thought about. I'm not sure.
There are definitely many ideas floating around in the physics community about what might lie beneath our current quantum picture. While no one has a definitive answer yet, here are a few speculative avenues that some researchers are exploring. Emergent reality. Some theorists propose that both quantum behavior and even space-time itself could be emergent phenomena. In this view, the way particles sample all possible paths might be a manifestation of deeper underlying processes, perhaps involving information or geometry at a fundamental level that we haven't yet uncovered. Hidden variables and determinism. Although traditional quantum mechanics rules out local hidden variable theories, as highlighted by Bell's theorem, ideas like the de Broglie-Bohm pilot wave theory suggest that there could be hidden dynamics guiding particles along definite paths. These theories are non-local, meaning they involve influences that aren't confined by our usual ideas of space and time, and they offer an alternative way of thinking about the choice of path, even if they're not mainstream. Retrocausality. Another intriguing, though controversial possibility is that effects might influence causes, what we call retrocausality. In such a framework, the outcome we observe could, in some sense, affect the history of the particle's journey. This might provide a different perspective on why all possible paths are sampled, but only one outcome is observed, though it challenges our conventional understanding of time. Quantum information as fundamental. There's growing interest in the idea that information itself might be the most fundamental element of the universe. In this view, the interference patterns and the summing over histories in quantum mechanics could be seen as nature's way of processing information. Each possible path might represent a state of information, and the observed path is the one that emerges from a kind of natural computation governed by quantum rules. Unifying quantum mechanics and gravity. Our current quantum theories work incredibly well, yet they don't include gravity. Many physicists suspect that a successful theory of quantum gravity, whether it's string theory, loop quantum gravity, or something entirely new, might reveal principles that explain why particles behave as if they take all possible paths. Such a theory could uncover new physical mechanisms that we haven't yet considered, which might even radically alter our understanding of reality. Each of these ideas is highly speculative and comes with its own set of challenges and open questions. The beauty and frustration of quantum mechanics is that while its mathematical framework is incredibly precise, its deeper meaning remains elusive. It's entirely possible that one or several of these speculative ideas, or something we haven't even dreamed of yet, could eventually provide a more intuitive understanding of why nature works the way it does. Does exploring these possibilities help spark any new ideas or questions for you?
I think time as we see it feels linear, going only in one direction. But maybe we just don't know how to access it better. So maybe one of these theories might be relevant. Who knows? And I don't know, I'm not a physicist and I'm not so deep into it. But when it comes to time, they say if you go at a very high speed, then the time changes. At least the time you feel changes. And that is also something that I just cannot quite comprehend. Because if it was linear, this shouldn't have happened. And I think there's also this one more thing, that the universe is wrapping around itself or something like that. So the time changes the farther you go from the gravity or the surface of the earth. I'm not entirely sure what that was, but something like that. So I think the whole concept of time that we people like me at least understand is not so straightforward. And I'm also now confused of one more thing, that if we say that each particle takes all possible paths, and then what we see is what the best path was, and this is on a microscopic level where we are seeing smallest particles. Now if the particle is big as us, how can we even test that I would have chosen one possibility out of thousands of other possibilities for the multiverse to even happen? Because multiverse could have happened if I really took them, but I did not. At least mentally I decided to take the best path. So I am following just one trajectory. But the particles, They work their own way. I just do not understand it.
Your thoughts touch on several deep and intertwined questions about time, quantum mechanics, and even our place in the universe. Let's break down some of these ideas. Time and its directionality, relativity and time dilation. Einstein's theory of relativity shows that time isn't the universal fixed flow we might imagine. When objects move at speeds close to the speed of light, or when they're in different gravitational fields, time dilates or passes at different rates. This means that what we experience as a linear progression of time can actually be stretched or compressed depending on the conditions. Experiments, like the Hafele-Keating experiment with atomic clocks on airplanes, have confirmed this effect. This suggests that time is more flexible and relative than our everyday experience might imply. Is time fundamentally linear? Some physicists argue that our perception of time's one-way flow, often tied to the idea of entropy and thermodynamics, might not be the whole story. There are theories exploring whether time might be emergent from deeper processes, which could offer new ways of understanding its nature. Although these ideas remain speculative, they open the door to the possibility that our conventional notion of time might be only part of a richer, more complex structure. Quantum paths in the macroscopic world. Quantum behavior at small scales. The principle that particles take all possible paths is a feature of quantum mechanics, observable primarily at the microscopic scale. In this domain, particles can exist in superpositions of states, and the interference between all possible paths results in the behavior we detect. This is well explained by the path integral formulation, where the probabilities of different paths interfere with each other. Decoherence and the emergence of a single trajectory. For larger objects like a person or even everyday objects, the situation is very different. The phenomenon of decoherence explains why quantum effects like superposition and interference become washed out. When you have countless particles interacting with an environment, the quantum choices collapse into a single classical outcome. Essentially, while the microscopic constituents might be exploring many possibilities, their interactions force the system into one dominant observed state. This is why we don't see a person taking all possible paths in any noticeable way. Multiverse and many worlds interpretation. The idea that all possible outcomes are realized in different branches, as suggested by the many worlds interpretation, is one way to think about the mathematics of quantum mechanics. In this view, while you, as a macroscopic being, experience one consistent trajectory, at the quantum level, every possibility is real in some sense. However, this interpretation remains just that, an interpretation, and isn't the only way to understand quantum phenomena. It doesn't necessarily mean that the multiverse is physically accessible or that it has observable consequences in our daily lives. Open questions and the frontiers of physics. Your curiosity about alternative explanations is exactly the kind of thinking that pushes the boundaries of physics. Some ideas still under exploration include emergent spacetime, the notion that both space and time might emerge from more fundamental, perhaps informational or quantum entanglement-based phenomena. Hidden dynamics. Speculative theories suggest there could be underlying dynamics or hidden variables, albeit non-local ones, that might give a different perspective on why we observe the path we do. While none of these ideas have been definitively proven, they represent ongoing efforts by physicists to reconcile the strangeness of quantum mechanics with our macroscopic experience of reality. Final thoughts. It's natural to feel both intrigued and bewildered by these concepts. The more we learn, the more we realize that the universe is not bound by our everyday intuitions. Your questioning, whether about the nature of time or the possibility that particles take all possible paths, mirrors the very spirit of scientific inquiry. Even without being a physicist, grappling with these ideas is a great way to explore the deep questions of existence. Does this help clarify some of your thoughts, or are there other aspects you'd like to delve deeper into?
I do have many thoughts and questions, but maybe I will ask you next time. There is so much about how the universe was formed and how the laws operate, and if you're supposed to know about it or not. There are many different topics that I want to think more about. But for now, I will take a break because I first need to at least absorb whatever you just told me. So I will talk to you next time.